All right, the review that I had planned, I can't find the document. It's the same problems, but the different highlights. So I may have to skip around a little bit. And we've got plenty of time, so we can do extras. Any questions or problems before we get started? Okay. Well, let me see. Let me mark everybody present first. All right. Well, let's get rolling. It's our last chapter, and this will be the only chapter covered on during finals week. And I assume everybody's going to take the exam in Brightspace. Is that correct? I see. There's one. Let me see. My chat. Okay, got a thumbs up from one. Thumbs up from two, three. Okay, everybody's gonna be in Brightspace. Okay. Well, in that case, what I'll do is I'll just zoom in from my office on next Monday, the 12th, in case you have questions. And then I won't even be in the classroom. All right, let's take a look at chapter 18, electrochemistry. The reaction of sodium bromide with chlorine gas to form sodium chloride and bromine. The appropriate half reactions are. All right, so we got to be able to write the compounds. Sodium bromide. Now, is that, it doesn't say, but I think this is probably a solution. And then chlorine gas, we're given that one. And then we have sodium chloride and bromine. Sodium chloride and bromine. What phase is bromine? Do you happen to know? It doesn't say, but under standard conditions, bromine is a liquid. So you're going to have a pool of liquid in the bottom of your reaction vessel. Okay, so in aqueous solution, these are going to be separate ions. And our oxidation states are 0 for these and charges for these. Okay, so the oxidation, we'll do that one first. Oxidation versus reduction. Okay, who's being oxidized? Who is losing electrons? Well, bromine has to lose electrons because it's a negative to go to a 0. So that would be bromine here. And that leads to this one. And it doesn't say what the phase is, so we can leave the phase out if we want. All right, so this half reaction, we have to lose electrons. That means electrons be on this side. Okay. That's one electron for each bromine, but there are two bromines. So we need two here on this side and two on that side. And that's balanced. So that just leaves, sodium is a spectator. We could leave sodium out. We're going from chlorine to chloride. Okay. That means we're gaining electrons to go from a 0 to a negative. but we have two of them. So we need two. Okay, we can't reduce those any further. If we look for the correct one, the oxidation should be, B looks pretty good. Yeah, B is a good answer. You'll notice one thing. We didn't have to go into the torturous procedure of adding oxygens and hydrogens because there were none involved. We could go straight to the oxidation reduction from the basic equation. Now this one's going to be a little bit different. Ammonium metavanadate reacts with sulfur dioxide. So ammonium is a spectator. That's why we don't see it in that basic reaction. So we have, let's see, this is number 2. VO3 minus. Okay. And then SO2 yields VO2 plus, VO2 plus, and SO4 2 minus. Okay, these have X's and Y's in front of them to show coefficients. The question is the ratio of X to Y. So that's what we're looking for. Ratio of X to Y equals what? Well, we've got to balance the equation to find out what that is. All right, so we're going to go oxidation and reduction. And we have to determine the oxidation states. So this would be 2 minus for the oxygen, be -6 total, but we have to hold one out for that one. So we're only balancing a -5, right? SO2, right, -4, so this is a +4. And then -2, there's only one of them. To be a +2, we need an excess of pluses. So we're going to have to balance those -2s with a +2, but we need 2 more pluses. So that's a +4 for that vanadium. And then -6 is all we have to balance here is to hold those 2 out. So that's a +6. Okay, now we have our oxidation states. Oxygen doesn't change. Vanadium goes one way, sulfur goes the other. So oxidation, which one loses electrons? Well, vanadium goes from +5 to +4. It has gained an electron. So sulfur must be the one that loses. SO2 yields SO4 2 minus with a +6. Okay, so that means metavanadate with a +5 here goes to VO2 plus, that's right, with a +4 oxidation state there. Okay, now we balance. The vanadium's balanced, the sulfur's balanced, so we go to the oxygens. We have 4 oxygens there, 2 here, so we need 2 more on this side. That means 4 hydrogens over here. Okay. We have 3 oxygens here and 2 there. That means we need 2 more on this side. Okay. Now we have 4 hydrogens. If we're going to reduce, that means we have to add electrons. So if we're going from a +5 to a +4, we only need 1 electron for each vanadium. For this one, we go from a +4 to a +6. We have to lose 2 electrons for each sulfur. Okay, so now we can balance electrons. So we just multiply this one by 2. And that's a 2 here. That's an 8 here, 2 here, and a 4 there. Now we could bring it down. We might be able to answer this without. So if we want the ratio of x to y, x is 2 and y is 1. Right? 2 to 1. It's the same on this side. X 2 to 1. Yeah, same. Okay, so we didn't have to finish we didn't have to bring everything down to find the answer. The answer here is 2 to 1. Okay. And the only thing that's going to allow you to solve that problem that quickly is practice. All right, number 3. The following reaction occurs in aqueous acid solution. In the balanced equation, the coefficient of water is, okay. So we have NO3 minus and I minus. Yields IO3 minus and NO2. So we need oxidation states. There's -1, and we have -2, -6 total, -5 is all we have to balance. So that's +5. This is a -2 times 3 is a -6. We hold one out. This is also a +5. Okay. So now we can decide which one's oxidation and which one's reduction. Nitrogen I left one out, sorry. -4, +4. Okay, so nitrogen goes from a +5 to a +4. That's reduction. We might as well put it in. So NO3 minus, that's a +5, goes to NO2, that's a +4. So this one must be the oxidation step. 5. Okay. 1 nitrogen, 1 iodide, we're good. Now we do oxygens, 3 oxygens. Okay. That means 6 hydrogens on this side. We have 2 oxygens there and 3 here. We need another one on this side. And that means we have 2 hydrogens on this side. Now we do electrons. We go from a minus to a +5. That is a loss of 6 electrons, right? You lose 1 to go to 0 and lose 5 more to go to +5. So we've lost 6 electrons on this side. Nitrogen, we've only gained 1 electron to do that. Okay? So if we multiply this one by 6, that should put us in good shape for adding. Okay? Now the question is waters. What's the coefficient for the waters? So we can just bring the waters down and deal with that. We have 3 waters on this side and 6 waters on this side. Right? So that one goes out and this one is 3. So the coefficient for water here is 3. All right, number 4. Let's see. Yeah, number 4. Let's see. Fluorine and water. Yields oxygen and fluoride. Okay, when the equation is balanced, the sum of the coefficients is. Okay. In basic solution, there it is. I was looking for what type of solution. This is basic solution. Okay, so we need the oxidation step and reduction step. That's 0, that's 0, that's -1, and this is a +1 and a -2. So in this one, oxygen is involved. Fluorine is involved. Fluorine goes from a 0 to a -1, that's reduction. So oxidation must be water. Water is involved in this one. Okay. All right. So let's balance the fluorines. That's 2 here. 1 oxygen here, 2 there. So we need 2 here to give us 2 oxygens. Okay. Now we balance from the rest of the, there's no oxygen here, no hydrogen. We've got oxygens balanced, but now we have 4 hydrogens that need to be balanced. Now we can go to electrons. Oxidation means we had to lose 2 electrons for each oxygen, but there are 2 oxygens. So that's 4 electrons. And this one, we gained 1 for each fluorine, but there are 2 fluorines. So that's 2 electrons. Okay? So if we multiply this one by 2, that should balance the electrons. 2, 4, and 4. And we're going to bring this one down so that we can convert it from acid to base. All right, we have 2 fluorines. Electrons are out. We have 2 waters. Now we have oxygens and 4 fluorides plus 4 hydrogens. Now we can convert it to base. So we're going to add enough hydroxyls to neutralize the hydrogens on that side and on that side. Okay, so now on this side we have 4 waters. On this side we have 2 waters. So these 2 waters go out, leaves us with 2 waters and 4 hydroxyls on that side. So when the equation is balanced, the sum of the coefficients. So we have a 2 plus 4 is 6, 7, 11, and 13. So 13 is our total. Let's see. Check my other copy. Yeah, I did 5 and 6 on my other copy. So we're going to go to the next one is 5. All right, the reaction below occurs in basic solution. What's the sum of the coefficients? All right, zinc and nitrate ions. Zinc, nitrate yields ZnOH 4 2 minus plus NH3. Do better than that. There we go. Okay. That's 0. -2, -6, -5. Here, +5. Let's see. This is +1, and this is -3. Now, hydroxyls are a total of a minus, right? So that's four minuses. We hold two of them out. We only have two minuses to balance, so that's a +2. All right. Okay, now we can decide. Zinc goes from 0 to +2. That's the oxidation step. And the reduction step then would be nitrate goes to ammonia. Wait a minute. That's not right. That was just to tally the oxidation numbers. So this one's -3. Okay, so we got one zinc here, one zinc there, one nitrogen, one nitrogen. Now we go to oxygens. We have 4 oxygens here. Okay, that's 8 hydrogens, but we've already got 4 hydrogens there. Right, so we're going to have 4 hydrogens on this side. Okay, and now we've got 3 oxygens here. We need 3 waters. That's 6 plus 3 is 9. We have 9 hydrogens on this side. Okay. Now electrons. We went from 1 zeros to a 2 plus. That means we lost 2 electrons. We went from a +5 to a -3. That means we gained 8 electrons. Right? 5 electrons gained to go to 0, and 3 more to go to a -3. So that's 8 electrons. Now all we have to do is multiply this one times 4. And we get 8 electrons. And 4. All right. The electrons are out. And we got 4 zinc. Okay. 4 zinc. We got 1 nitrate. We got 16 waters. We have 9 hydrogens. Okay. 1, 2, 3, 4. 1, 2, 3, 4. Then we have zinc on this side. 4 zinc 2 hydroxides. And let's see. This NH3 plus 3 waters plus 16 hydrogens. Okay. So we can cancel things out and then do the hydroxyls, or we can do the hydroxyls now and then cancel things. Let's do the hydroxyls first. If we cancel these hydroxyls, these hydrogens, we need 9 OH minus, which gives us 9 waters, in addition to these 16 on this side, and we need 9 hydroxyls over here. But we also need 16 hydroxyls over here. Right? That cancels out and leaves us with 16 waters, but we also have 16 hydroxyls going in over here. Okay. Now, this makes 25 waters here and 16 waters there. So those 16 waters are gone, and we just cancel these. That leaves us with 9. The water molecules we cancel. hydroxyls, we have 9 on that side and 16 on this side. So those cancel, and 9 from 16 is 7. Okay? So, reaction blurs, some of the coefficients. All right, so we have 4, we have 1, we have 7, we have 9. On this side, we have 4, 1, 3. That's it. 4, 1, 3. So that's 8, 17, 24, 25, 29. 29 is not there. Okay. I think I know what happened. This, we could write this one as plus 4, like that, 4 hydroxyls. So if we do that, those 4 hydroxyls come down here. Let's see. What did we do to them? We multiplied 4 times those. So those are actually 16. All right, 4 times 4 is 16 hydroxyls. So we have 16 hydroxyls here, and we have 7 here. So that makes those go away, and that's 9 on this side. So let's add that up again. We still got 4 here, 1 there, and 9 here. Then we have 4 zincs. We have 1 ammonia. Oh, 3 waters. Let's try that again. Okay, so we got 4, 1, yeah, 6. And then on this side, we have 4 zincs. We have 9 hydroxyls and 1 ammonia. And that's it. So that's 10, 20, 26. No, I'm still wrong. All right, what am I doing wrong? That's number 5. Okay, 4 zincs, that's right. 6 waters, yep, 6 waters. 1 nitrate, yep, 1 nitrate. 7 hydroxyls. Okay. It says there's 7 hydroxyls still on this side. And on the other side, we have 4 zinc hydroxyls. Okay. Let's cross that one out, at least 4 there. 1 ammonia. Yep. Is that it? That's it. So that would be 5, 11, 18, 19, 23. All right, I don't think we have time to go back and do that one all over again. Let's say that's a good candidate for an extra credit. Thing don't want to come off. Let me check something out before I go any further. Okay. Number 6. When the following reaction is balanced in acidic solution, what's the coefficient of iodine? All right, this one should be fairly simple. Died. 2. Okay. That one's 0. Let's see. This one should be +5. So the oxidation step, we're going from this iodide losing to go to that iodine. And the reduction, I know why I put this one in here, because these iodines are converging on that one product. So this one with a +5 is also going to that one. All right, so we have 2 iodines here. We have 1 and 2 there. Now we have oxygens, no problem there. 6 oxygens here. Okay, that means 12 hydrogens. And yeah, we are in acidic solution. Okay. Now we do electrons. So for each iodine, we had to lose an electron. But there are 2 iodines. So we lost 2. In this one, we had to go from +5 to 0, which means we gained 5 electrons for each iodine. Right? But there are 2. So that means there are 10 electrons. Okay, we need 10 electrons up here. So that's just a multiplier of 5. 10, 5, and 10. Okay, question was coefficient of I2. All right, so we got rid of these. And let's see, we got 10 iodines and something. Okay, we're going to bring them down. Let's bring them down. So we have 2 iodates. We have 10 iodides. We have 12 hydrogens. And we have 6 I2s. And we have 6 waters. Okay, I see the problem now. This can be reduced further. If we divide everything through by 2, then we get 1 here, we get 5 there, we get 6 there, we get 3 here, and we get 3 there. That's why the coefficient of I2 is 3. All right. Number 7. For this equation, which of the following are the correct half reactions? Okay. 2 Fe2 plus. Fe2 plus and Cl2 yields 2 Fe3 plus and 2 Cl minus. Okay. correct half reactions. All right, it doesn't say which is which, so we just say, we'll go first one oxidation and the second one reduction. So we went from 2 plus to a 3 plus means we lost electrons. 2 Fe 2 plus goes to 2 Fe 3 plus. And reduction must be this one. Let's do Cl, oops. Cl minus. There we go. So we lost 1 electron for each iron, but there are 2 of them. And we gained 1 electron for each chlorine, but there are 2 of those. Right? So if we well, the proper half reactions then would be we've got 2 electrons on each side, but we have, let's see. If we're only sticking with the half reactions, we're not bringing them down yet. The half reaction for iron could be reduced by a factor of 2, right? Divide by 2. And that's the half reaction for iron. We can't do that with this one because that's a coefficient of 1, 2, and 2. So the oxidation step is Fe2 plus yields Fe3 plus 1 electron, which is 4. And this one would be 1. So 1 and 4 are the correct answers. Okay. How many electrons are transferred in the following reaction? Now, why would we want to know that? If we want to use the Nernst equation, we have to know how many electrons are transferred. How many moles of electrons? That's a term in the Nernst equation. So we want to find out how many electrons are transferred. Let's see, number 8. Let's write the equation first. 2ClO3. I suspect this equation is already balanced. And plus 10 iodide yields 5 iodine, chlorine, 6 H2O. Oxygen 6. Yep. 2 chlorines. Yep. 10. Yeah, that's balanced. Okay, so what we need to know is 0, 0, minus 2 plus 1 plus. This is going to be minus 5. That's all we need there. Okay. So let's try this with tie lines. Maybe we can figure out, since it's already balanced, we can probably figure out how many electrons are transferred. So if we go from chlorine here to chlorine there, that's a loss. Right? That's a loss. How many electrons? Plus 5 to 0 is loss 5 electrons per chlorine. But there are 2 of them. So that's 10 electrons lost. Right? If we go from this one to this one, that's a gain of 1 electron. Excuse me. My mistake. That's the gain. That's gain 5 electrons per chlorine. This is a loss. Loss of 1 electron per iodine times 10. 10 iodines equals 10 electrons. So 10 electrons. Yeah, 10 electrons. were transferred in this equation. Let's see, the next one I have marked is number 10. All right, determine the number of electrons transferred during the reaction when balanced. Okay, so this equation is not balanced. We have to do that first. So let's see. AuCl4 minus, that's a complex ion. Yeah, that's what that is. Complex ion. That's copper. And then gold, fluoride ions, and excuse me, that's copper, not chromium. Copper 2 plus. Okay. Fluorides are spectators. Okay. But the gold, since this is a -1, we have to assume it's a -1, otherwise we can't calculate gold. So that's -4 total. We hold one out. Let's see. Yeah, we hold one out. That's a +3. How do we know? A +3 and a -4 is a -1. Okay, this is 0. This is 0. -1, 2 plus. We don't care about chlorine because it's a spectator. So, oxidation step, reduction step. If we go from +3 to 0, that means we gained. So, let's see. Number of electrons transferred. All right. I'll tell you what, I'm going to take that gold out. Keep it separate. Right, that simplifies the matter because chlorine's a spectator. And this is a reduction. Right, so the oxidation must be copper. Okay. There are no waters involved, no oxygens, no hydrogens involved. So we can go to electrons, right? We had to lose 2 electrons. And here we had to gain 3 electrons. Okay. So how do we balance? Cross multiply. Just like that. Which means, let's see, is that going to set us up for let's go ahead and do this, 6 and 3. And this will be 2, 6, and 2. We bring them down, 2, 3, 2, and 3. Okay, so we can't reduce it any further. Right? The number of electrons we see here, that's the number that's transferred, 6 electrons. I was looking for a gotcha in case you bring them down and then you have to reduce them further by some factor. But we didn't in this case. All right. Number 11. Number 11. Consider the galvanic cell based on the reaction Fe2 plus dichromate ion, Fe3 plus, and the chromium 3 plus ion in acidic solution. What's the voltage of the standard cell carrying all this reaction? Okay, in order to do that, we need to know what are the half reactions, and then we can go to our chart and find the standard reduction potentials for each one. So let me see if I can do this from there to here. Oxidation, reduction. Actually, yeah, Yeah, we can do it this way. So Fe2 plus to Fe3 plus means we lost an electron. Fe2 plus to Fe3 plus means we lost an electron. That's oxidation. The Cr207, Cr207 2 minus. Let's see, go ahead and do this one. Minus 14, minus 12. So this one's plus 6. And then Cr3 plus means we had to gain 3 electrons per chromium, but there are 2 of them. Right? So that's 6 electrons. So that's the reduction step. Okay. So let's go to our, now that we have split them apart, now this one's going to have some built-in waters, but we should be able to find it without that. Let's go to our table. I'll come back to 11 after we find the values. Okay, keep going, keep going. Here we go. All right. So iron 2 plus, iron 3 plus. We're going to look for iron 3 plus electrons on the left-hand side. Iron 3 plus, nope, that's Fe. That doesn't work. Let's see, iron. It's not on this side. Iron 2 plus. Already looked at that one. 3 plus, nope. Where is it? Iron 3 plus 1 electron. Is there another one down here? Nope, that's it. That's the whole thing. Okay. Ah, there it is. Okay. So the reduction potential here is 0.77. 0.77 plus. So if we reverse it, that means the charge has to be reversed. So this should be a minus as written. So let's go to dichromate yields chromium 3 plus. That should be easier to find. Dichromate sticks out like a sore thumb. Dichromate. Here it is. Dichromate to 3 plus. Okay. So this standard potential is 1.33 volts. Okay, that works. We add those together. I don't even trust myself to add today. .56 volts. That's the potential for that cell. And let's go back up to 11. Oops, too far. Too far again. And there we go. So plus 0.56 volts. That's your answer. All right. Let's see. 13. I got 13 marked next. The anode in a voltaic cell. I think this is the definition. Anode in a voltaic cell and in an electrolytic cell is, okay. In a voltaic cell, the anode, well, actually the anode is by definition the site of oxidation in both of them. The site of oxidation. Anode by definition is the site of oxidation in any cell, voltaic or electrolytic. It's just when you take a voltaic cell and you run it backwards, now the anode is switched and the cathode is switched. So the definition stays the same no matter what. That's D. D is the best answer there. Okay, let's see. Yep. 14's next. A strip of copper is placed in a 1 molar solution of copper nitrate and a strip of silver in a 1 molar silver nitrate. The two metal strips are connected to a voltmeter by wires, and a salt bridge connects the solutions. The following standard reduction potentials apply. Okay. Which of the following statements is false? Okay, so we have standard conditions for a silver copper voltaic cell. First one says electrons flow in the external circuit from the copper electrode to the silver electrode. All right, so what we need to do is say which one's the anode and which one's the cathode. All right, so look at the voltages. If we make the silver cell negative by flipping that to an oxidation step, then our cell is negative. So we need to flip the copper to a negative. That makes the copper the anode. Right? That makes copper's the anode and zinc is cathode. Right? So this is the side of reduction. And this is the side of oxidation. Right? Electrons always flow in an external circuit from anode to cathode because they're losing electrons here and we're gaining electrons here. So it flows from anode to cathode. So we're going to have electrons flow in the external circuit from the copper to the zinc. A is true. B says the silver electrode increases in mass as the cell operates. If electrons, oh, wait a minute, silver and copper. This is silver. Am I still true? Yeah, it's still good. Okay. Silver electrode increases in mass as the cell operates. Yes. The cathode, by receiving electrons, it is reducing silver ions to silver metal. And those silver metal atoms are plating out on the electrode. So it does increase in mass as the cell operates. That's only for cells where the electrode participates in the reaction. If you have an inert electrode, then you don't get any change in mass for the electrode. C says, there's a net general movement of silver ions through the salt bridge to the copper half cell. Well, no. The silver ions are being consumed by reduction and plating out on the electrode, so they don't move any. All they do is they go to the electrode. Right? So C is false. Right. The other two should be true. Negative ions pass through the salt bridge from the silver half cell to the copper half cell. Negative. Right. Okay, look at it this way. If electrons are flowing that direction, then we're going to try to build up, let's see. Yeah. We're going to try to build up negative charge on this side in this cell. If we try to build up that, then the only way to balance it is to move negatives out of that cell toward this side. So any negative ions that are in this cell will move through the salt bridge to the copper. That's how you keep the charge balanced. Right, so that's true. And some positive copper ions pass through the salt bridge from the copper half cell to the silver half cell. Okay. So as we're moving negative ions this direction, then positive ions accompany parallel these through the salt bridge to accompany those electrons. So that was true also. The whole idea here with the salt bridge, well, actually two things. The salt bridge is required to complete the circuit, right? You don't get an electrical current if a circuit is broken. And you want to balance charges because we don't build static charges in chemistry. Only the physics does that. Chemistry, we balance our charges. Okay. What's that doing there? Okay. 15. Let's see, 15? Yeah, 15. Which of the following species cannot function as an oxidizing agent? B, C, D, and E. All right, so we need sulfur, NO3 minus, NO3 minus, dichromate. This one's +6. I know that one already. That one's a -1 and MnO4 minus. So this is -8. Hold one out. That's a +7. Okay. And this one is -6. Hold one out. +5, and this one's 0. Okay. If something's going to function as an oxidizing agent, it must be able to be reduced. Right? Can we reduce this one any further? We're looking for the one that cannot function. Yes. This one will function as an oxidizing agent because it can be reduced. This one can also be reduced. This one can be reduced. This one can be reduced. That one cannot. It's got as many electrons as it's going to hold. You cannot reduce that one any further. Right? Iodine needs one electron to look like xenon. So iodine picks up that one electron, and its electronic configuration now looks like xenon, and it has a full complement of electrons in its shells. So it doesn't want any more. Right? So you're not going to reduce that one. It's not an oxidizing agent. Number 16. I think. Let me check my. I've got two systems going on here. Yeah, 16. Okay. Which metal, aluminum or nickel, could reduce zinc 2+ to zinc metal if placed in the zinc 2+ solution? All right. Okay, so we have, well, rather than write those on the board, we have reduction potentials. So which metal could reduce zinc, right? So what we need is a positive voltage that's equal to or greater than -0.76 in order to reduce it. So we need to be able to flip the charge, flip the voltage in sign, so that we get a combination that's greater than 1, a positive value. So if we did that with nickel, right, that would make a +23, 0.23 for nickel. Right, now nickel is being oxidized. And then the -0.76, -0.76. Right, that's still a minus. But if we did aluminum, that's 1.66. Aluminum is 1.66, and minus 0.76. That value is positive. Aluminum will do it, right? It can reduce zinc. Because if aluminum is oxidized, it generates a plus 1.66 volts, balanced by negative 0.76 for the nickel reduction, and the cell is spontaneous. Right? So the answer there is aluminum. Aluminum only is the only one that will do it. 17. Let's see. Well, let's see. 17. Just a second here. Bromine. I'm going to skip that one because I want to go to this one, number 18. And I think I've got several based upon this this voltaic cell. Yeah. 18, 19, 20, and 21, and 22. All those are based upon this cell. 18, 19, 20, 21, and 22. We may not get to all of them, but we're going to start with this one. Okay, refer to this cell, and the contents are written for each one. The question is, what's the voltage? What's the standard? E0. That's the standard cell potential for this cell. All we have to do to answer that question is to say which one is the anode and which one's the cathode. Now, you can't just assume, I mean, it's supposed to be that the right-hand side is the cathode and the left-hand side is the anode, but it may not be, right? Not everyone adheres to that standard. So we look at the potentials, right? The one on the left is the first one, 1.506, and the one on the right is 1.330. All right, so if we make the right one, the left one, negative as the anode, then it doesn't work. So this cell is written backwards. All right, what we have to do is make the chromium cell negative. We have to make it the anode. So 1.506 minus 1.330. There we go. That's 0.176 volts. That's C. Yes, that's correct. That's the standard potential. Okay. All right. So let's go to number 19 and say, when current is allowed to flow, which species is reduced? Okay. We've determined that the one that's reduced is the cathode, and the cathode is the one where we did not change it, right? The cathode is the manganate ion to manganese 2 plus. So the species that's reduced is the MnO4 minus. Okay, MnO4 minus, that's 19. That one is reduced. And in particular, the manganese in that molecule is reduced. All right. We're looking at the same cell. And what we want to know now, what is the value of Q, the reaction quotient for this cell reaction? All right, so this is going to take a little more work. Let's see, we're down to 20. what we've got to determine is what is the balanced equation for this entire galvanic cell. Then we have the values, the concentration values given for the cells, and we can put them in the correct location in our calculation of Q. Right? So let's see. We have the two equations there. Yeah, we have the two equations. So we just flip the chromium equation and we keep the MnO4. Right? MnO4 minus, yeah, plus 8H plus 5 electrons yields Mn2 plus and 4H2O. Okay, and this is reduction. So the oxidation is the other one flipped. 2Cr3 plus, 2Cr3 plus, and 7 waters yields Cr2O7 2 minus plus 14 hydrogens plus 6 electrons. 6 electrons. Okay. 2 or 5, 5, 1, 2, 3, 4, 5. Okay. So now we have to bring these together. Okay. So this is MnO4 minus and 2Cr3 plus and 7 waters and 8 hydrogens and just a second. No, can't do that yet. Sorry. We got 5 electrons here and 6 there. So we need to multiply this one times 6. And this one times 5. Okay. So this makes that one 6. This is 48. This is 30. This is 6. This is 24. Okay. That makes this one 10. This one's 35. This one is 5. And this one is 5, 270. And this one is 30. Okay. So the electrons go out. Now we can add them together. All right. So we have 6 MnO4 minus plus 10 Cr3 plus plus 35 water plus 48 hydrogens. On this side we have 6 Mn2 plus 5 Cr2O7 minus 24 water and 70 hydrogens. Now let's reduce it. We have 35 waters here and 24 there. So we get rid of those, and that makes 11 waters here. Hydrogens, 48 on this side, and that would be 22. Yeah, 22 left over. Okay, can we reduce it any further? 6, 10, 11, 6, 5. No, that's as far as we can go. So now what's the Q? Well, the Q is going to be products. Actually, it's not square brackets, that's equilibrium. Like that. To the 6th power. And then Cr2O7 2 minus to the 5th power. And then hydrogens to the 22nd power. It's getting ridiculous, isn't it? MnO4 minus to the 6th power, and then Cr3 plus to the 10th power, and then water. Wait a minute, water's pure. We don't include water. Right? We don't include water because it's a pure liquid. Right? So that's it right there. Now we need to plug in the values. So what's the concentration of Mn2 plus? Mn2 plus is 0.20 molar to the 6th power. Dichromate ion. Dichromate is 0.3 molar to the 5th power. Hydrogen ions. They're the same on both sides, 0.01 molar to the 22nd power. And then the manganate ion is 0.1 molar to the 6th power. And then chromium 3 plus is 0.4 to the 10th power. Okay? All right. So let's do some number crunching. To the 6th power. So find my right key here. There we go. 0.3 to the 5th power times that one. 0.01. Yes. To the 22nd power. That's that one. Then 0.1 to the 6th power. Divide that into it. And 0.4 to the 10th power. Divide that into it. So I get 1.48 times 10 to the minus 41. Rounded off, 1.5 times 10 to the minus 41. Okay? That's a lot of work just to get that one answer. All right, what does that mean? That means if this Q is very small, that means the reactant side is extremely small and the reaction is going to move. Well, actually, we don't know what the K is. Right? The K is probably very large. Right? We learned that. The K is usually very large for these galvanic cells. So that means it's going that way, lickety split, with a voltage of, what did we say before? 0.164. All right. Now, this one says in the balanced reaction, what's the stoichiometric coefficient of H plus? The stoichiometric coefficient, all right, H plus is 22, right? 22. We did that already. That's 20, 21. We got that. And one more. This one says, what's the cell potential at 25 degrees? Okay. So we need the Nernst equation, correct? The Nernst equation. Let's see. It's in useful information. All right. It's in useful information. 22. Rather than flip through E0 minus 0.0591 over N. Is it minus? Yeah, 0591. over N times the log of Q, correct? Log of Q. Okay. So let's see, what was the standard potential? Let's see, that would be 1.506 minus 1.330 is 0.176. 0.176 volts minus 0.0591 over N. Now, how many electrons actually are moving? We crossed them out to get to where we are. 30 electrons. 30 moles of electrons. And then the log, let's see, I'm going to have to erase this, times the log of 1.48 times 10 to the minus 41. There we go. So I'm going to take the log of that first, since it's already here in my, let's see, let me flip that. I'm going to take the log of that, and then 0.0591 divided by 30 times that, and then change the sign. Yep, and then 0.176. So I get 0.256. All right. 0.256. Yeah, E. Round it off. 0.26. Okay. So that's why I wanted to stay on this problem all the way through that sequence, because we calculated information that we needed to solve the last problem. Okay, let's see. 23. 23 is not marked on this one or that one, so I'm gonna skip that one and go down to, let's see, 26. 26. There we go. Let's make some room. Okay. 26. Copper will spontaneously reduce which of the following? Okay. So if copper will reduce something, that means it has to be oxidized. So we're talking about copper going to, let's see, 2 plus, right? 2 plus. That's the only thing it can do. Okay, so we need a potential for that one. And then we need potentials for the others. If they're to be reduced, then they have to go, let's see, what do we have? Have Fe2 plus and Ag, silver, Fe2 plus, silver 1 minus, aluminum 3 plus, all right? Okay, so those are the only three. What we need is standard potentials for these reductions, right? Reduction potentials. Okay, so let's look them up. We'll go down to Here we go. All right. Silver, 1+ reduction. Silver. Here it is. Silver is 0.80. Okay. Fe2+. Now, I'm thinking here, we're talking about going to the metallic. Right, so this one's going to silver, this one's going to iron, this one's going to aluminum. We're going all the way. So that means Fe2+ here with 2 electrons goes to iron. Fe2+ goes to iron, which is, oh, these things are in my way. Fe2+ to iron is minus 0.44. Minus 0.44. And aluminum is below it, minus 1.66. Okay. Oh, and copper goes to copper 2+. Copper 2+. Copper 2+. Here it is. Copper 2+, 0.34. Now this is going to be negative 0.34. Right? Because that quoted in the table is the reduction potential. So that one has to be negative 0.34. Yeah. Okay. So if copper will oxidize itself at that value, which one of these can we combine it with to make a positive outcome? Only this one. Silver. Let's see. Back to 26. Let's go back up to 26. Here we go. Only silver. That's the only one that we can combine this one with this one as a reduction and get a positive voltage. The others give you negative voltage. Copper will not reduce them. Okay, 27, 28. 28 is my next one. That one's getting weak. Go to a fresh one. Put these there. 28. Which of the following is the best reducing agent? Which one oxidizes with the highest negative voltage? All right. A, B, C, D, and E. You have Cl2, H2, G, 2+, and Cl-. Which is the best reducing agent? Which is oxidized? Oxidize the best. All right, so what we need to do is look at the reduction potentials and then flip the values. So we got to go down to the chart again. And here we go. All right. Chlorine. Here it is. Was 1.36, so it'd be minus 1.36. Hydrogen 0, right? Because hydrogen's the standard electrode. It's always 0. Magnesium. So let's see. let's take magnesium. Magnesium. Well, we're going to have magnesium on the right-hand side, I think. Magnesium. All right, where is it? Look again. Be methodical about this. There it is. Okay. Minus 2.37. So this one would be plus 2.37. This one will be minus 2.37. Right? No. You can't oxidize that one any further. Right? That one just it will not work. You can't oxidize magnesium any further, right? Because it's already lost the 2 electrons that makes it look like neon, right? It's perfectly happy. It's not going to function as a reducing agent anyway, right? So we can throw that one out. And then the chloride is not going to, well, let's see. Chloride might have something to go for it. Let's see. Chloride would be minus, wait a minute, oxidized. Chloride oxidized would be minus 1.36. Chlorine reduction. Wait a minute. We're using the same. One of them has to be positive and one's negative. If this one is, if positive 1.36 is this one, Cl2 plus 2 electrons yields Cl minus, like that. And that's a plus 1.36. All right, but we want to oxidize. Can we oxidize this any further? Take electrons from it. I don't think so. I don't think you can oxidize this one any further. Unless there's one in here. Can we do? No, because you have to add. No, that one won't work. For similar reasons. All right, so we're really comparing these two. And the one that's the best, the strongest oxidized is the one with positive value. That one right there, magnesium. That's the best oxidized reducing agent. It's the best oxidized one. All right, let's see, where was I? 28. Go back up. 28. 29. No, 30. We're going to do 30 next. Okay. Following has a potential of 0.92 volts. Okay, notice that you're reducing mercury 2 plus to mercury 1 plus. And you're using it against the standard hydrogen electrode. So we're reducing mercury 2 plus. That means it's against the standard hydrogen electrode. So that means its standard reduction potential is 0.92 volts. if the concentrations of the ions are 1 molar and the hydrogen is at 1 atmosphere, then E0 for the half reaction is plus 0.92 volts. That's definition of standard reduction potential, right? So that's D, 0.92 volts. This question is just to check to see if you really understand what we mean by standard potential against the hydrogen electrode. Let's see. Okay. 33, we're going to skip those. Let's see, 34. 34. So we're going to do 34 next. For a reaction in a voltaic cell, both enthalpy and entropy are positive. That was positive. That was positive. Which of the following statements is true? E0 will increase with temperature, decrease and change whenever the G's for all temperatures. Okay, well, if this is positive, that means our reaction going from something to something, that's a positive value. That means it's endothermic. It's on this side, right? So if we increase the temperature, what will happen to E0? Well, if we increase the temperature, we're going to shift to products, right? We're going to move it to products, and we're going to decrease the voltage. That's not, no, that doesn't work. Okay, let me see where I went wrong. 34. That's what I get for trying to be logical. We need something more than that. All right. Okay. Let's take another approach. All right, we know that delta G0 equals delta H minus T delta S. So there's our temperature term. Okay. We also know that delta G0 equals minus NF E0. So there we get this part incorporated. All right. If we combine those two, that is, if this one's equal to that and this one's equal to that, then these two are equal. So delta H0 minus T delta S0 equals minus NF E0. Okay. Yeah. So we can't cancel any terms. This is not going to change. That's not going to change. These are positive. That's positive. That's positive. Right. And this would be a constant term. So what happens when we do something to temperature? If we increase the temperature, So we're going to increase the temperature. That makes this one more negative. We reduce this term. It makes it more negative, which reduces the overall term. So we're decreasing this side, right? Because we're making this one more negative. We're decreasing this side. This one then will making this one more negative than if this one increases, that will make this term more negative. Right? This one's going more negative. We want this one to go more negative also for the balance. So this one has to go up to accommodate that negative. That's where we get the increase in voltage based upon an increase in temperature. Right? So A is true. B can't be true because A is true. E0 will change. Yeah. Delta G0 is greater than 0 for all temperatures. Not necessarily. If we make this temperature low enough, then this value goes so low that this one has to be, E would go negative. So we found our answer. A is the answer. It took more work than I thought it would, but we got the right answer then. All right, let's see. 35. We're going to do 35. Standard free energies of the formation of several species are. What is the standard reduction potential of methanoic acid in aqueous solution? All right, standard free energy. Okay. We did this one before. We put this one on the board. Equals negative NF E 0. Okay. So if we find out the free energies formation, if we find out this value from that equation, then we can find out this one as long as we know how many electrons are transferred. And the equation is given there. So 4 moles of electrons are transferred. That's 4 here. Right? What's F? Let's see. F is where is it? Here it is. It is 96,485 coulombs per mole. And then E0. What we need, see, that's kind of confusing. What we need is this value right here, delta G. So we take our equation and we say products minus reactants. So products, methanol is 1 mole at minus 163. Minus 163 kilojoules, right? Or is that joules? That's kilojoules. Times 1 mole, so that's all we need there. And then the second term is water, minus 237. There's 1 mole of that. So minus 237. Let's say that's plus. And then we subtract the reactants. So 1 mole of methanoic acid, minus 351.1. Minus 351.2, excuse me. Okay. And then we have hydrogen ions are 0, electrons are 0. That's it. Okay. So delta G0 is going to be positive 351.2, and then 163 minus and 237 minus. That doesn't look right. Hold on a second. 351, 351.2, and then 163 minus 237 minus. That's better. So this is minus 48.8 kilojoules. Right. And this has to be in joules, right? It needs to be in standard units, which is joules. So this would be minus 48.8 times 10 to the third joules, right? Minus 48.8 times 10 to the third joules. And if we solve for E, then we would have minus 48.8 times 10 to the third joules divided by, these come under here. This is a negative. So that's a negative 4 times 96, 485 mole. Okay. So let's see if that works out. See, this needs to be times 1,000. And then 496, 485. So that's 0.126 volts. Yeah, 0.126 volts. Okay, that's an awful lot of work just to get that one simple answer. Okay, let's see. 36. That's also on my agenda. See how we doing on time. Coming up on 10 o'clock. Okay, we're still in the lecture part. So we have these values for the reduction potentials of copper 2 plus and lead 2 plus. For a galvanic cell employing these two, right, copper and 2 plus and lead and 2 plus, calculate the maximum amount of work that would accompany the reaction of 1 mole of lead under the standard conditions. Under standard conditions. Okay, so we can find the standard voltage of the cell. Right? All we have to do is decide which one needs to be the cathode, which one's the anode. Right? If we make copper the cathode, then that makes it negative, and a negative gives you it gives you an electrolytic cell if you run it backwards. But we need to flip the lead. The lead becomes the cathode. So that's 0.342, and then plus 0.130. So the lead cell becomes the cathode. Right? And that gives us 0.472 volts. Okay, that's E0. All right. Maximum amount of work. The maximum amount of work is the free energy. Right? It's the free energy for this cell. So delta G0 equals negative NF E0, right? Well, actually, we calculated a different formula that works just as well. Minus Q E max. So W max equals minus Q charge times E0. Okay. So in this case, we found out what E is. Now what we need is okay, the charge that's transferred. This has to be in coulombs. Right? And the reaction that we're working with is not. So if lead is going to be oxidized, that means lead has to be on this side, right? And electrons have to be on that side. Okay, this is the oxidation step. The reduction step then would be the copper. Copper 2 plus electrons equals copper. Okay, so this is going to be 2 electrons here and 2 electrons here. Right. So lead, let's see, do I need to go that far? No, we just need to know how many electrons per mole of lead. So it's 2 electrons per mole of lead. Yeah. Yeah, 1 mole of lead. That the problem says that. So what we've got is 1 mole of lead is being oxidized, and 2 electrons are being produced for every 1 mole of lead. 2 moles of electrons. And then the Faraday converts that 96,485, is it? Yeah, coulombs per mole. Yeah. 96,485 coulombs per mole of electrons. Okay, so that cancels moles of lead, moles of electrons, and leaves us with the charge that's being transferred. All right, I calculated. Well, that's just 2 times that value. So this is 1.93 times 10 to the 5th coulombs. So negative 1.93 times 10 to the 5th coulombs times 0.472 volts. So I get minus 9.11 10 to the 4th joules. Maximum work. Yep. Or, see, our answer is in kilojoules, isn't it? Okay. So this would be, take 3 of those to make kilojoules, and then the other one makes this one minus 91.1 times 10 kilojoules. 91.1 kilojoules. That's the maximum amount of work. And remember, maximum work is equal to the maximum free energy. So free energy has to be negative in order to be spontaneous. So this is correct. This is going to be a negative value. It's spontaneous at 91.1 kilojoules. All right, let's see who's next. That was 36. Yeah, I got 37 marked off also. 37. Car battery consists of 6 identical cells, each of which carries out the reaction as written. The value of E0 for such a cell is 2.039 volts. Calculate delta G at 25 degrees for the reaction. That should be simple, right? That should be simple. We just need to know how many moles of electrons move. Right. So we got lead and lead 4 oxide. And let's see, can I do it that way? I'm gonna have to split these. So let me go ahead and do this. Oxidation step, reduction step. All right, oxidation. Which one loses electrons? Well, the lead metal loses electrons and goes to lead 2 plus. Goes to lead SO4. And loses electrons. So it loses 2 electrons for each one of these because this one is 2 plus and this one's 0. The other cell goes from PbO2, which is 4 plus, and it also goes to SO4. But this has to add 2 moles of electrons. Now let's see, based upon the equation, right, we have one lead going to one of these, the other lead going to that one, so that's why we have 2 of these, but the number of electrons transferred is 2. We have 2 moles of electrons transferred. So if we're going to calculate delta G0 minus NFE0, then the N is equal to 2. Right? And the F is 96,485. And then the E0 is 2.039. Right? So delta G0 should be simple to calculate. 2.039 and 96,485 and 2 is minus 3.93 times 10 to the 5th. Oh, this is joules. So it would be minus 3.93 times 10 squared kilojoules, which would be, bring these 2 over here, minus 393 kilojoules. C, that's the closest one. 93.5. All right. Okay, who's next? Let's see, I went down to 39 next one. Yep. 39. Okay. All right, 39. The following reaction refers to this system. 3 silvers plus 1 nitrate yield and plus 4 hydrogens yields 3 silver ions plus nitrogen oxide gas and 2 waters. What's the equilibrium constant? Okay. If this system is at equilibrium, then we know that calculating the Nernst equation says E equals E0 minus 0.0591 over N times log of Q. Right? But if that's K, then this one has to be 0. You have no cell potential for a cell at equilibrium. So now we have 0 equals E0 minus 0.0591 0.0591 over N log K. Okay, that's where we're headed. We just need to know what E0 is now. Okay. E0. We want to know, oh, it tells us which one's the anode and which one's cathode. Okay, so all we have to do is add those two together, right? 0.9636, 0.9636 volts, and then minus 7990 volts. And that'll give us the standard cell potential. And that's 0.1646 volts. Okay. Oh, we got to know how many electrons are moving. We have to know that. So if 3 silver atoms become 3 silver ions, that means we had 3 electrons, right, for the silver. If this equation is balanced, it should be the same thing for the nitrogens. So the nitrogens go from here to here. This one is, let's see, -2, this is +2, and this one is +5. So yeah, it had to add 3 electrons, and silver had to lose 3 electrons. Okay, so this value is 3. So let's see, 0.1646 minus 0.0591. Is that right? Yeah. And then this is 3, and that's log K. Okay, so we're going to put this one on this side, minus 0.1646, and then divide by this term. What is that term? This is 1.97 times 10 to the minus 2. So that becomes over here. This minus comes over here. 1.97 times 10 to the minus 2 equals the log of K. So let's take, let's see, 17, 2. Yep, let's divide those. So this is 8.355 equals log. Okay, we need the anti-log of this value. So it's 10 to the 8.355 equals K. And K, if I calculate it right, 2.6, oops, 2.27 times 10 to the 8th. Yeah, there it is. B. B is your answer. That's a huge value, right? Which means that this reaction really wants to go to the right. In fact, almost to completion, essentially to completion. All right, that was 39. Let's see. 4. 44. Go. That. Oops. Losing that one. Let me get another marker. B4. Okay. An excess of finely divided iron is stirred up with a solution that contains copper 2+ ion. System is allowed to come to equilibrium. The solid materials are then filtered off and the electrodes of solid copper, solid iron are inserted into the remaining solution. What potential develops between these two electrodes? This is a trick question. If the system is at equilibrium and you introduce those electrodes, your voltage is going to be 0. You get nothing from it because the system was at equilibrium when you finished it. All right. 45. All right, concentration cell is constructed with copper electrodes and copper 2+ in each compartment. In one compartment, the copper is 1 × 10⁻³ molar, and the other compartment is 2 molar. Calculate the potential for this cell at 25 degrees. The standard reduction potential for copper is 0.34. Okay, which cell is going to be the anode and which cell is going to be the cathode? The anode cell is going to be the low concentration because since it's lower than the other side, it's going to try to balance the concentrations between the two. So the low side is going to come up, the high side is going to come down as you're taking copper ions from solution and plating them on the electrode. That concentration goes down. That's the cathode side. All right. So let's see. Here we go. Okay, so again, we have, let's see, E0 minus 0.0591 over N times log Q. Yep. How many electrons are moving? Well, to go from Cu 2+ to Cu is 2 electrons. This is going to be 2. Then what's the E0? Well, the E0 is 0. Right? Standard potential, if they were both at 1 molar, it would be 0. So this term goes to 0. What we need to know is Q. What is Q? All right. If we, let's see, 45. Okay. So if we wrote this equation out, so that we had copper 2+ and copper on both sides, right? Then we have copper 2+ and copper on both sides. Then which one goes to which? Well, the cathode goes from this 2+ to that copper. Right? So that would be the cathode. This would be the anode because it's going from copper to 2+. But these coppers are metals. They don't count. So this is the copper anode divided by the copper cathode concentration. That's what this is. This is equal to, this is the anode concentration divided by the cathode concentration. Okay? So that means this potential is going to be minus 0.0591 divided by 2, and log Q then would be the anode concentration, which is the low one, at 1 × 10⁻³. And the high one is 2 molar. You see that? So there's our equation. Let's see, exponent runs divided by 2, and then take the log of that. So this term right here is negative 3.301. And that's negative times negative. This is going to be a positive voltage. So we're going to get a positive voltage out of it. It's going to be spontaneous. Times 0.0591 divided by 2. And this is 0.0975 volts. Or 0.098. That's it. Okay. All right. It's 45. Very often the voltage for concentration cells is not reported in voltage, but in millivolts. So 0.098 volts would be 98 millivolts. I just move the decimal 3 places to the right. Let's see, next one, yeah, 46. Do 46. Okay, using the following data to calculate solubility product for lead sulfate. Refresh my memory on that one. Okay. Well, this is the lead acid battery, isn't it? Yeah, that's the lead acid battery. Okay. Okay, for the solubility product, the solubility product is an equilibrium value. So we're looking for the equilibrium, the K, from this reaction. And to do that, we need to know what the standard potential is. Yeah, we need to know what the standard potential is. Now, the actual potential would be 0. E is 0, but E0, the standard for this one would be, let's see. No, this is not the lead acid battery, because if we take the second equation and make it minus, then we're going to get something a lot less. Okay, so what's the E0 for this one? The E0 is going to be 1.69 minus 1.46. So that's 0.23 volts. That's the E0. And let's see, the number of electrons moved, N equals 2, right? Okay. Two, three, yeah, that's so far so good. So if that's true, and E equals E0 minus 0.0591 over N times log of Q, we did this before. This is going to be 0. So that means E0 is going to be 0.0591. This came over here as negative, that's negative, so I just threw the negatives out. This is going to be 2, and this is log of K. So this value is equal to 0.23. So I just need to get everything on this side. So this is going to be 0.23 times 2 is 0.46 and divide by 0.0591. So that's 7.783. And then K is going to be 10 to the 7.783 power. Right? Yep. So this is 6.07 times 10 to the 7th. That's the K for the reaction, but we're looking for the KSP. And the KSP okay. This reaction lead sulfate. The KSP is going to be this one, lead sulfate. Let's see. Yeah, that's right. Is going to be this one, 2 plus, and sulfate, 2 minus. But the way the reaction is set up, we're going from this side to that side. Right? We're going from sulfate ions. Well, sulfate doesn't participate, it's the lead. So the lead 2 plus is going from lead 4 plus to 2 plus. It's on the wrong side. So what we have to do is flip that reaction. And if this is the K, then the KSP is going to be the inverse of the K, which would be 1 over 6.07 times 10 to the 7th. Now let's take the inverse of that. So this is equal to 1.65 times 10 to the minus 8. Or 1.7. Okay. I don't know, did I explain that well? Let's see. Yeah. When we combine these two reactions, which side is the solid on? Well, we flipped the bottom one. So that put the, that still kept the PbSO4 on the right-hand side. Right? That's the wrong side. It needs to be on the left-hand side to make ions. So we found the K for that reaction, but the solubility product would be the other way, right? Lead 2 sulfate to the ions. So that's why I had to flip it. I had to take the inverse. All right, let's see who's next. You did that one. 47. I do want to get to 47. Let's see. Which of the following statements is or are correct? B, C, D, and E. All right. Let's see. At least 2 of the above choices are correct, so we got to look at all of them. The value of E0 is equal to 0 in a concentration cell, and the value of E is equal to 0 in any cell at equilibrium. Yeah, that's true. Both of those statements in A are true. B, the value of E0 can be equal to 0 in a concentration cell, and the value of E must be equal to 0 in a concentration cell. The value of E0, it is. E0 is equal to 0 in a concentration cell. The value of E doesn't have to be equal to 0. No, B is false. That second part of that one just wipes that one out. Right, B is false. The value of E0 and E are equal to 0 in any cell at equilibrium. No. E0 is based upon 1 molar concentration. E can be any concentration. So E0 at equilibrium, E is 0. That's true. But E0 is a non-equilibrium situation. So that was also false. E0D. E0 can never be equal to 0. Right, so that was false. And the only one that's true is A. All right. Let's see, we're going to skip down to 49. Yeah, 49. You make a cell with an aluminum electrode in aluminum nitrate and a zinc electrode in zinc nitrate. If you could increase the concentration of aluminum 3 plus, which of the following is true about the cell potential? All right. So, let's brute force this one. If we're going aluminum electrode to aluminum 3 plus, or let's do it reduction potential first. All right. We're going aluminum 3 plus 3 electrons yields aluminum solid. Zinc 2 plus. Yeah, it has to be. Yeah. Zinc is 2 plus. 2 plus 2 electrons yields zinc. And let's go ahead and get the standard potentials for this situation. Let's see, so I don't have to look it up. Minus 0.76 for zinc. And aluminum would be minus 1.66. 66 volts. Okay. So which one becomes the cathode? This is cathode. This is the anode, because changing that sign gives us a positive sum. So now we're going to have aluminum on this side yields aluminum 3 plus 3 electrons is plus 1.66 volts. Okay. So the standard potential for this cell is going to be 0.90 volts. Yeah, plus 0.90. That's the standard potential. Okay, we may not need it, but I'm going to do it anyway. So if we take that situation and we combine these two equations, we're going to have to balance the electrons. We don't have to worry about hydrogens or oxygens. So we're going to balance these two. This one has to be multiplied by 3. This one by 2. So 6 electrons are moving. N equals 6. And we combine the two. 3 zinc 2 plus 2 aluminum yields 3 Zn solid plus 2 Al 3 plus. Okay. So if we want to calculate the Q value, let's see. Actually, okay. If we want to calculate the actual potential for this cell, we need the Nernst equation minus 0.0591 over n, and n equals 6. So we'll go ahead and put that in there. And E0 is, we're going to put that one in there too. 0.90. All right. And then this is going to be log of what? Log of Al3, 3 plus squared. And then this is going to be Cn 2 plus to the third pi. Okay. So let's see, how far do we need to go with this? Oh, standard conditions. Yeah. If we're starting off with standard conditions and we're saying, all right, what happens if we increase the concentration of aluminum, which is the following in true? Well, if we're starting off at 1 here and 1 there, right, which would be standard conditions. What would happen if we increased the aluminum concentration, right? If this started increasing above 1, then what would happen to this term? This term would be greater than the log of 1 plus, be greater than 1, which would be this whole term would increase. Right? As this one increases, this term increases also. So that would increase this term, that would increase this one, make it more negative. The voltage would decrease. If we increase aluminum, the voltage would decrease. Okay? Right. That's how we do it mathematically. Now, if we go back and look at the balanced equation, what happens if we increase this on that side? What does Le Chatelier say? He says if we increase that, we're going to drive the reaction equilibrium back that direction, right? Which would decrease the voltage. Right? We're going the wrong direction. We need to go this direction for increasing voltage. This direction decreases voltage. So either way, you get the right answer. Right? Voltage would decrease. Cell potential would decrease. 51. Now, if you do it mathematically, then you can actually calculate what the voltage would be. But to answer that question, we can use Le Chatelier and get the same answer. All right, 51. Let's see. What is the value of the reaction quotient for the voltaic cell constructed from the following 2 half cells? When zinc concentration is 0.0103 and silver concentration is 1.35 molar. All right, we got to find out which one. First, we have to find out which one's the cathode, which one's the anode. All right. All right. So which one do we have to flip? They're both reduction potentials right now. Which one has to flip in order to, which one changes sign in order to give you a positive voltage? The zinc has to become the anode. So that means zinc is on this side, right? And it makes zinc 2 plus 2 electrons, right? And its standard potential is 0.76 now. And then silver stays the cathode, right? Silver plus an electron yields silver solid, and its value is 0.80. So that gives us 1.56 volts. E0. All right, how many electrons are transferred? Well, all we have to do is that, and that. Now these are equal. So N equals 2. 2 moles of electrons. Okay. So remember when we were before, when we had, if we bring these down, then the anode is on top, anode concentration on top, cathode on the bottom. And then this one is 1 coefficient, this one's 2. So if we do this one, E0, 1.56, no, sorry. E, is that the question? Oh, what's the value of Q? Okay, so Q is simply going to be this concentration over this concentration squared. Okay, so it says that zinc is 0.0103 molar, and silver is 1.35 squared. So I get 5.65 times 10 to the minus 3. Okay, that was easy enough. All right, let's see, who's next? 52. All right, which of the following statements is true concerning the electrochemical cell described below? All right, let's put that up here. Copper 2 plus. Copper 2 plus at 0.816 molar. Okay, salt bridge. Then this is copper. This is a concentration cell. 843 molar. This is copper. All right. Okay. So this should be the cathode. And this should be the anode. The cathode in a concentration cell, in order for it to be spontaneous, has to be greater concentration than the anode. That's a greater concentration than the anode. right? That's good because electrons are going this direction, right? When you write this line notation, it has to be anode, cathode. There are no exceptions, right? So the cell reaction is spontaneous with a cell potential of what? Well, yeah, it's spontaneous. Now we have to calculate the cell potential, right? A, B, and E say it's spontaneous. So now we have to calculate what is the cell potential. Well, if it's a concentration cell, then E0 is 0. So E equals minus 0.0591 over how many electrons? 2, right? Go from that to that, it's 2 electrons. And then we have the log of the anode over the cathode, 0.816, 0.843. Okay. My guess is this is going to be in millivolts. So if you're in a hurry, take B. 0.816 enter 0.843, divide, take the log of that, then 0.0591 times 2 divide. So this is 4.18 times 10 to the minus 4 volts. Or if we take 3 of those and make millivolts, then this is times 10 to the minus 1, 4.18. So 0.418 millivolts. There it is, B. Yeah, B was a good choice. There. All right, that was 52. Who's next? 53. 53. Go. 53. Consider the hydrogen-oxygen fuel cell. Okay. With a delta G of that value, which of the following statements is true? Let's see. Which of the following statements is true? All right. Oxygen, gas, water. That's not balanced. There, that's balanced. It doesn't change the delta G 0 because these are standard conditions. Equals minus 237.18 kilojoules per mole of hydrogen. Okay. Which of the following statements is true? All right. At standard conditions, the maximum work the fuel cell could do on the surroundings is 237.18 kilojoules per mole. Well, that's true, right? It says on its surroundings, which means it's negative, right? Remember system, surroundings. If the work goes this direction, then that value is negative. So yeah, it does that much work on its surroundings. A is true. A is true. How about B? In the real world, the actual amount of useful work for the cell can can do is less than. That's also true. We're talking reality here. C, more energy is dissipated as waste heat in the fuel cell than in the reversible pathway. Well, yeah, when your reaction is reversible, then you can expect to extract that much work from the cell, right? But if it's not reversible, which is all real cells, then you lose to heat. You lose to entropy and heat, right? So that's also true. So A, B, and C are all three true. That means D is your answer. That all three of those are true. Let's see. 56. Okay, 56. Excuse me. All right. How many moles of electrons are produced from a current of 14.4 amps in 3.2 hours? Moles of electrons. All right. What are we starting with? 14.4 amps. 14.4 amps, which is equal to 14.4 coulombs per second. That's what that means. An amp is 1 coulomb per second of current in a conductor. So if that's our starting point, then I'm going to take the time first. Let's find out how many coulombs of charge in 3.2 hours. 3.2 hours. Well, that's the wrong units, right? We need to convert those units. So if I need to cancel hours and end up with seconds, how many seconds in an hour? Well, let's see. 60 minutes in an hour, 60 seconds in a minute. 60 times 60 is 3,600. There we go. Now we need to convert coulombs to moles of electrons. And for that, we need the Faraday constant. So 96,485, is it? Yeah, 96,485. Coulombs per mole of electrons. That cancels that and that. So now we've done all the thinking. We just need to crunch some numbers. 14.4, 3.2 times that, 3,600 times that, and 96,485 divided into that. And I get 1.1, no, 1.72 moles of electrons. Okay? That's just unit conversions. Let's see, who's next? 57? Yeah, 57's on my other list. An antique automobile bumper is to be chrome plated. The bumper, which is dipped in an acidic dichromate solution, serves as the cathode of an electrolytic cell. The atomic mass of chromium is 51.996 grams per mole. 1 Faraday equals that. If oxidation of water occurs at the anode, how many moles of oxygen gas will be evolved for every 151 grams of chromium deposited? Okay. I think we probably need some stoichiometry here. Yeah. So the bumper is serving as the cathode. So cathode means reduction. And we've got this in solution, 207, 2 minus, and it's leading to chromium metal. All right, so this is 0. And this is, let's see, we did this one before. This is +6. Okay, so that's the reduction side. The oxidation side is where water is oxidized at the anode. So how do we oxidize water? Well, water is, let me see, do we want to do both of them? No. Under acidic conditions, we're going to produce hydrogen ions plus oxygen gas. Okay, that's one of the keys to doing this problem. We're not actually splitting the water molecule into hydrogen gas and oxygen gas. We're keeping this in acidic solution with only oxygen gas produced. So this is the oxidation side. All right. So we need 2 chromiums here, right? We need 2 hydrogens here, and we need 1 oxygen there. Okay. Let's see. So, okay. This is already balanced. We need to balance those 7 oxygens here. That means we need 14 hydrogens on this side. Now we need electrons. Okay. Hydrogen didn't change. It's a plus here and a +1 there. -2 to 0. This one did change. Right. So we lost. I'll tell you what. Let's keep these whole numbers. 2 and, oh, excuse me, 4. That's better. I don't like to use fractions unless I have to. In this case, I didn't have to. Okay, so we got 4 hydrogens there, 2 oxygens. That's good. Now let's do electrons. So if we went from +6 to 0, that means we had to add 6 electrons for each chromium, but there are 2 chromiums. So that's 12 electrons. And we lost on this side. We went from a -2 to a 0, which is 2 electrons lost, but we got 2 of them. So we have 4 electrons lost on that side. Now we just need to balance. So let's say 3 times that would give you 12. So this is 6. This is 12. This is 3. And this is 12. Okay. Now that we've got the combined equation, that'll give us our stoichiometry. So let's put this all together in one equation. We don't have to include the electrons. We know how many electrons were transferred, of course, 12 electrons, in case we need them in the future. But we have 1 dichromate, right? We have 6 waters. We have 14 protons. Now we have 2 chromiums on this side. We have 7 waters. And we have 12 protons and 3 oxygen gas. Okay. Now let's see. These 6 go away, and that leaves us with 1 here. These 12 go away, and that leaves us with 2 here. So that's our balanced equation that we can do some stoichiometry with. All right. I'm still on 57. Okay. How many moles of oxygen gas will be evolved for every 151 grams of chromium? So if this is 151 grams of chromium, right? And the question is moles of oxygen. Okay, so if we want to go from here to here, we need moles. So 151 grams of chromium, we want to convert that to use the molar mass, which was given to us, wasn't it? 51.996. So that's the moles of chromium. That's 2.885 moles of chromium. Now we're going to convert that to moles of oxygen. So oxygen from chromium, we have 3 here and 2 here. So 1.5 times that is 4.33 moles of oxygen gas. Rounding error. Unless I calculated it wrong. No. There's a rounding error in there. Best answer is A, 4.36 moles of oxygen gas. 59. Let's see, we skipped 58. Yeah, we skipped 58. We're going to 59. Let's see, coming up on 11. Let's see, how am I doing on? Okay, it's doable. 59. All right. Electrolysis of a molten salt with the formula MCl using a current of 3.86 amps for 16.2 minutes deposits 1.52 grams of metal. Identify the metal. All right. If the molten salt is MCl, that means that metal has a +1 charge. That's it. All right. So if we're going to deposit the metal, we have to reduce the metal by 1 electron for each 1 mole of electrons for each mole of metal. Okay. All right. So let's see. 1.52 grams of metal. If we want to know what that metal is, what kind of information do we need? The only way we can identify the metal is, well, 2 ways. One, if we know the atomic number. There's no way we can get the atomic number from this information. How about the molar mass? That is a possibility. So in order to do the molar mass for this metal, we need to know mass and moles. So the moles of metal, we got the mass, right? 1.52 grams. 1.52 grams. How many moles does that represent? Well, if we know how many moles of electrons were used, that's equal to the moles of metal. So we just need to find out how many moles of electrons were driven through that medium to produce this mass of metal, right? So if we've got 3.86 amps, 86 amps would be coulombs per second, all right? Coulombs per second. And how long did we go? 16.2 minutes. Right, we need to convert that to seconds. Right, minutes, seconds. 60 seconds in a minute. Minutes cancel, seconds cancel. Okay, now we've got coulombs. We need to convert coulombs to moles of electrons. 96,485 coulombs for 1 mole of electrons. Right, so that takes care of that one and that one. And this will give us moles of electrons. 3.86, 16.2, 60 times 96,485 divide. So this is 3.89 times 10 to the minus 2 moles of electrons, which is also moles of metal because it's 1 to 1. Okay, 3.89 times 10 to the minus 2 moles. All right, 1.52, divide that into it. This gives us 39.1 grams per mole. So we go looking for it. 39.1. That's potassium. Right, off the periodic table, that is potassium. Okay, who's next? 60. 60. If an electrolysis plant operates its electrolytic cell at a total current of 1.8 times 10 to the 6th amps, how long will it take to produce 1 metric ton of magnesium from seawater containing magnesium 2+ ions? All right. So here's what we're doing. We're going to reduce magnesium 2+ to magnesium metal. Okay. All right. And how much are we going to produce? 1 metric ton. A metric ton. 1 metric ton equals 1,000 kilograms, which is equal to 1 times 10 to the 6th grams. Right, 1,000 times 1,000 is 1,000,000. Why did I do that? Because we need to use the molar mass of magnesium. Right? So if we're going to produce this many grams of magnesium, we want to know how many moles of magnesium that is. So that we can do the stoichiometry, right? Oops. There we go. So magnesium is 2431. Like that. That'll tell us how many moles magnesium. 1 exponent 6. 24.31. This is 4.11 times 10 to the 4th moles of magnesium. And it takes 2 electrons for each. So that's equal to 8.23 times 10 to the 4th moles of electrons. Okay? Moles of electrons. So 8.23 times 10 to the 4th moles of electrons is how many coulombs? Right? 1 mole of electrons equals 96,485 coulombs. Okay. Okay, if that's how many coulombs, let's go ahead and do that one. 96,485. It's going to introduce some rounding error, but I think the logic is going to help us better. 7.94 times 10 to the 9th coulombs. Or that's, coulombs. Right. That's the total current, total charge. Right. If we're moving if we're moving 1.8 times 10 to the 6th amps, 1.8 times 10 to the 6th amps, 1.8 times 10 to the 6th amps is coulombs per second. Right? So if we divide this into that value, coulombs will cancel and tell us how many seconds. Right? Coulombs cancel. Denominator of the denominator is the numerator. And that's 4.41 times 10 to the third seconds. Now we need to convert that into what are our answers? Hours, days, minutes. Okay, we'll have to do let's do minutes first. Right? 60 seconds in 1 minute. Okay, 60 divided into that. That's 73.5 minutes. It's not there. Right? 73.5 minutes. Okay, let's change that to hours. 60 minutes, 1 hour. Okay, 60 divided into that. That's 1.22 hours. 1.22 hours. 1.2 hours. There it is. A. Okay, there you got it. All right. Understanding the chemistry here is important, right? That's how you make your first step. But unit conversions takes you the rest of the way. Okay, let's see. I'm going to skip down to 65. If there's nothing on this one between us and them. Oh, 64. We'll do 64 and 65. What mass of chromium could be deposited by electrolysis of an aqueous solution of Cr2SO4 sub 3 for 145 minutes using a constant current of 11 amps? Okay, this one should be fairly simple. If we're going from Cr2, SO4 is a spectator. So what's the charge on Cr2? Cr2 SO4 3. Well, this one has to be 3 plus because this one's 2 minus, right? 2 here, 3 there. So it's actually Cr 3 plus 3 electrons yields Cr solid. That's what we're interested in. Okay, what mass of chromium? If we go 11 amps for 145 minutes, 11 amps, coulombs per second. We need minutes. 60 seconds or a minute. And yeah, and then 145 minutes. 145 minutes takes out the minutes and leaves us with coulombs. We'll go ahead and do that much. So this is 8.70 times 10 to the third coulomb. Now we can convert that to electrons. 96,485 coulombs per 1 mole of electrons. And then we might as well go ahead. Moles of electrons. How many moles? 3 moles of electrons for every 1 mole of chromium. Let's go ahead and do that. So divide by 96,485 and divide by 3. That gives us 3.0056 times 10 to the minus 2 moles of chromium. All right, what was the question? Grams. Yeah, what mass? Okay, so we need molar mass now. Moles, grams. Chromium is 51,996. 51.996 grams. And that's equal to 1.56 grams. All right, what went wrong? 17.2 grams. Wait a minute. Did I look at this wrong? Hold on a second. 11 coulombs. $60.5 times and then 11 amps. Oh, I calculated wrong here. 11, 60, 145. That's it. This is 9.57 times 10 to the fourth. I don't know what happened. Then divide by 96,485 and divide by 3. 3.306. 3.306 times 10 to the minus 1 times 51.996 is 17.2. Okay, got a math error here. Okay, 65, I think. Yeah, 65. Which of the following used to be more precious than gold or silver due to difficulties in refining it? Okay, this is just a memory equation. That's aluminum. Before Hall and Herold came up with their electrolytic process for refining aluminum, aluminum was produced in very, very small quantities. So it was worth more than gold. Okay. Let's see. That's all I have in that one. Let's see if there are any more on this sheet. Oh, yep. Short answer. Okay. Balance the following equation. I think we did this one already. Yeah, we did this one early on. All right, you've already got this one in the acid solution. We don't need to beat that horse again. 72. We haven't done this one yet. Balance the following. So we'll do 75. Okay. BiOH3. BiOH3. And SNO2, 2 minus. 2 minus. Yields. Bismuth. And SNO3, 2 minus. And I assume it says base means basic solution. Yeah, okay. This is going to be basic, right? These hydroxyls are in solution. So if we've got these and no hydrogens left over, then we're in basic solution. All right, so let's do the oxidation step and the reduction step. And we need, this is 3 minuses, so that has to be a +3. This is 2 minus plus 2, 0, and this is plus 4. Okay, I'm sure you can figure that one out. Oxidation. All right, SN 2 plus to 4 plus, that's your oxidation step. All right, and this goes to NO3, 2 minus, and this is a plus 4. Okay, then that means bismuth hydroxide going to bismuth is a reduction. Okay. The non-hydrogen oxygens are balanced already, so we'll go to the oxygens. There are 3 on that side, 1 on this side. So we need 1 on this side, and we need 2 hydrogens on this side. Then we need, we got 3 oxygens on this side. We need 3 oxygens on this side. That means 6 hydrogens over here. This is an oxidation, so the electron's going to be on that side. We went from plus 2 to plus 4. That's 2 electrons. We went from plus 3 to 0. That means we added 3 electrons. Okay? So 3 and 2, multiply that one by 3 and this one by 2. So we have 3, 3, 6, 3, and 6. And this is a 2, 12, 6, 2, and 6. Okay. And we'll bring it down to Bi OH3 plus 3 SnO2 2 minus, and 3 waters, and 12 H pluses. Okay. This side, let's be the bismuth first. Bi, then 3 SnO3 2 minus. Yep. And then see, I put water next. 6 waters and 6 hydrogens. Okay. Let's see if I'm coming along all right so far. Just to save us time that I don't make mistakes. Okay, now let's combine terms. We got 3 waters here and 6 there. Those go out. This becomes 3. We got 12 hydrogens here and 6 there. Makes this 6. And those are gone. All right. So if I add hydroxyls here, 6 hydroxyls plus 6 hydroxyls on this side, that makes 6 waters, right? And okay, something went wrong. Let's see, reduction step. BiO. Okay, I made it more complicated than it needs to be. Yeah, It shouldn't be. Okay. Let's back up. Let's get rid of that. Let's go back. All right, let's go back and start over with this one. All right, one bismuth, right? Yeah. 3 oxygens and 6 hydrogens, right? No, that's my mistake right there. We've already got 3 hydrogens, so we only need 3 more. There we go. This is reduction, so we do have 3 electrons here. Okay. Now we multiply this one times 2. So that's a 2 there, 6 there, 6 there, 2 there, 6 there. Okay, now we're back on track. All right, we've got 2 BiOH, 3 and 3 SnO2 minus, 3 water, 6 hydrogens. There we go. Now 2 Bi and plus 3 SnO3, 2 minus, and then 6 waters and 6 hydrogens. Right there. Okay. These go out, leaves us with 3. 6 hydrogens are gone. That's it. We got our basic solution here. The hydrogens are gone. So we should have 2 bismuth hydroxide, 3 SnO2 minus, 2 bismuth element, 3 SnO3, 3 waters. That's it. But a big mistake was I didn't consider those hydrogens when I was bringing these over. That was the problem. Okay, that's it. Sharing is stopped. Okay. Any questions? All right. Well, let's see. All I need from you guys now, besides the last exam, is your last lab report and your last notebook check, and that can be submitted in Brightspace. Okay. Well, I don't know about you, but I'm exhausted.